we looked once upon a time at kinetic energy. This video is going to be about rotational kinetic energy. Now, kinetic energy worked out pretty well because we said it was energy due to the motion of an object, and that was mostly true. But what if we have an object like this? We've got a bar and it's rotating. There is some kind of motion, but there's not motion of the center of mass of the object. The object itself is sitting still. Or maybe we've got a wheel, right? Maybe we've got a wheel like this. And we are allowing that thing to rotate. Again, the wheel itself isn't going anywhere. The center of mass is stationary, but we've got motion about the center of mass, like around it. So this has a different kind of kinetic energy, and that's rotational kinetic energy. We had before, for linear terms, kinetic energy was half mv squared, and so far we've been able to get away with just making direct substitutions. We're going to be able to keep doing that. Rotational kinetic energy is going to be half, instead of mass, we're going to look at moment of inertia, and instead of a linear speed, we're going to have a rotational speed. So rotational kinetic energy is just half I omega squared. If I have an object that's spinning, I'm going to have a half I omega squared type of rotational kinetic energy. If I have an object that's moving along, I get this half mv squared. If I have an object that's rolling, then I have half mv squared, and I also have half I omega squared. I have both. So when I do a problem that involves energy conservation, I can consider both of those. If I have an object sitting at the top of a hill, let's give this a gamma, an m, and an r, and we'll give the hill some height h. This object is going to start from rest, roll down the hill, and I want to find its speed at the bottom. So I'm going to do this problem exactly the same way I had done it before. I'm going to say I have initial energy, I have final energy, I have potential energy, I have kinetic energy, and I have now rotational kinetic energy. I need a spot that I'm going to call 0, so let's call the ground h equals 0 at the bottom. My initial potential energy is still mgh. My final is still 0. That was easy. My initial kinetic energy, I'm not moving yet, so that's 0. My final, I'm going to have a half m v final squared, and I don't know my v final. And then I've got a rotational kinetic energy. In the beginning I'm not spinning yet, afterwards I am. So I've got a half I omega final squared. Now to actually solve these problems, I'm going to need to be able to do a little bit more and make some statements about how v and omega are related. But this is the major idea. I need to be able to just do a regular conservation of energy problem, but I'm going to tack on the one extra term for rotation. Now here's another piece. I have this idea of rolling without slipping. What that means, if I've got an object like this and I make a mark on it right here, if I let the object roll, then a moment later, that mark is going to be on the ground. Right, now that mark is in contact with the ground. Still rolling. And a moment after that, that mark is now off the ground. So I'm rolling to the right, object keeps rolling, the ball keeps rolling, my mark makes contact with the ground, and then it keeps rolling, and my mark is off the ground. This is not sliding relative to the ground at all. I don't have any sort of side-to-side skidding motion. Maybe rolling without slipping is actually easiest to understand by looking at the opposite. The opposite of rolling without slipping would be rolling, well, with slipping. This is what happens when it's icy out and you are trying to get your car moving. You step on the gas and your tires spin, but you're not going anywhere. Your tires are slipping on the ground. When you roll without slipping, that means that your tires are gripping the ground well, and if you were to put, I don't know, a piece of paper underneath your car, the piece of paper wouldn't tear. It's not being dragged around. It would just get run over. If you have gone bowling, when you go bowling, you throw the ball and it slides for a minute, right? When it lands on the alley, it's moving forward, it lands on the alley, and it just kind of slides for a second. And then after, I don't know, a few feet, it starts rolling. When it's sliding like that, it's because right now it has too much translational kinetic energy for the amount of friction that it gets. There's not a whole lot of friction. Right now it's moving too fast, so that sliding is a stretch where the ball is slowing down. I throw the ball. Ooh. I don't know. Like that. I feel like probably wearing some kind of a hat. I don't know. Not really a bowler. I throw the ball. It goes up and lands. Right, here's the line, and this is very slick. And then the ball just kind of like slides for a little while. And then at some point, it seems to get enough grip on the ground to where it starts to roll. Once it's at this point, now we are rolling without slipping. And when we roll without slipping, we are not losing any energy. For this stretch, we might start to roll a little bit, but we are definitely slipping. And if we are slipping, we are losing energy. The reason all this matters is that when we are rolling without slipping, we can say this. We have a rotation, and we have a radius of the wheel, or of the object. It could be a cylinder or something, right? And we're moving along this way. Our rotational speed happens to be equal to r times omega, and it's because this is our fixed point down at the bottom. So this is kind of our axis, or this is kind of our axis, and this is kind of our distance from the axis. So the tangential speed of that point would be like saying we're making a circle around the axis of rotation this way, and a piece on the edge of this would be moving at a speed, a linear speed of v equals r omega. If you don't quite get why this is, it's okay to say, you know what, I know the speed of my center of mass of a ball is going to be equal to r omega when I roll without slipping. Now I told you that this was an important thing, and now I want to go back to why it is. All the way back to here. If I'm looking at this rolling without slipping situation, then I could do a little bit more. Because if V equals R omega, then I can say omega final equals V final over R. Let me show you why this matters. My total energy on the left is mgh. My total energy on the right, half m V final squared plus half I omega final squared. I'm going to put in that omega final is V over R. So over here I'm going to get a half m V final squared plus a half I, which is gamma mr squared, times omega final squared. So V final squared over R squared. Well, I have an R here that can cancel with an R here, or an R squared and an R squared. And that gives me mgh equals half m V final squared plus half gamma m V final squared. I now have an equation that only has the one missing variable. I'm going to go a little bit farther and factor V final squared out of those. So left side mgh, right side I actually get a half m V final squared, and left out of this front term is 1, left out of the second term is gamma. Mass drops out, which is important. I wanted mass to be able to drop out of this thing because I didn't care about the mass when this thing was a block sliding. So I was hoping to not care about the mass now. I get V final equals 2gh over 1 plus gamma with a square root. If I am not rolling, if I'm sliding only, and there's no friction, then gamma is 0, and I get exactly what I had before. For this thing to work, for the ball to roll, I need there to be some amount of friction. So when we do problems like this, you will see phrases like, there is sufficient friction to ensure rolling without slipping. If there's no friction at all, I'm not going to lose energy, but it's going to be really strange. The ball is just going to slide down the ramp like a bowling ball would. The ball is just going to slide down the ramp and not roll at all. So if we have enough friction so that we can roll without slipping, then we still won't lose energy. But when we have a block that just slides down without friction, we get a square root of 2gh. When we have something that rolls without friction, this gamma means that we're moving at a slower speed at the bottom, which means it's going to take longer to get there. It takes longer to roll than it does to slide. If we have an object with a smaller gamma, so like a solid sphere has a gamma of 2/5 for a solid ball, where if we have a hollow ball, that's 2/3. For a solid ball, gamma is smaller. The bottom of this fraction is smaller, so my V final gets to be a bigger number. For a hollow ball, V final will be a smaller number. So a solid ball, a smaller gamma, will win the race. that's rotational kinetic energy and rolling without slipping together. I will do an example video to work through an actual problem, but this covers most of it.